Greetings everyone, this is our presentation for our final project of master's degree, Recognition and Translation of Sign Language based on Deep Learning for Deaf and Mute Individuals, presented by me, LEMDANI Koceila and OULD TALEB Dyhia, supervised by Mr. Kheyreddine Djouzi. This is our plan for this presentation. First of all, the introduction. We know that communication is crucial for human life, as individuals cannot survive alone and must interact with others, using sound as a medium of transmission. Speech enables the sharing of ideas and thoughts. However, for deaf and mute individuals, communication occurs visually through sign language, which conveys meaning to those who understand its significance. So, problem statement. However, when deaf or mute individuals want to communicate with people who do not understand sign language, this is where the problem arises. This is precisely the issue we aim to address by facilitating communication between these two groups. So, our objective is to create an application that takes an image and returns the corresponding alphabetical letter according to sign language. So, what's sign language? Sign language is a language used by deaf or mute individuals. Unable to hear speech, they use visual communication to convey meaning to others, primarily through signs and body gestures, especially with the hands and arms, but also through facial expressions. A gesture is a hand movement that can be a sign, but a sign can include symbols, images, and other elements. So, what are the characteristics of sign language? The configuration, the shape of the hand, the orientation as we see in the pictures, the movement, and the location. What are the challenges in translating sign language? Sign language vary depending on the regions. So American Sign Language is different from French and British and so on. Like spoken languages, each sign language has its own vocabulary, which adds complexity to detecting all the signs. The coordination between the two hands to create certain sign, as well as the synchronization of movements, adds a layer of complexity to the model. The methods used and the methods that exist. To process the images, we used convolutional neural networks. Examples of this type of architectures include EfficientNet by Google, VGG by Oxford, ResNet by Microsoft, Inception by Google, YOLO by Ultralytics. The datasets we used are synthetic ASL alphabet, English alphabets, trained with RoboFlow, ASL dataset, also RoboFlow, and ASL and Arab Sign Language and ASL and Indian Sign Language. So our first approach, YOLO V10, you only look once. YOLO is a convolutional neural network designed for real-time object detection by predicting bounding box coordinates and object classes in a single pass. To adapt YOLO for sign language gestures recognition, a custom dataset was created and annotated with bounding boxes. Each image is accompanied by a file containing the object class and bounding box details. Center coordination, width and height for training the model in YOLO format. The input image is divided into SS grid of cells, for example 7x7 or 13x13. The convolutional layers of the model extract relevant features from the image, such as edges, shapes, textures, colors, intensities, etc. Each cell in the grid predicts a certain number of bounding boxes, typically fixed number like 2 or 5, for the object detection. It also calculates the confidence score, the probability that the box contains an object, and the class probability. To eliminate redundant boxes that overlap significantly, the model selects the box with the highest confidence score. Second approach, DenseNet SVM, a hybrid of two methods, DenseNet for feature extraction and SVM for classification. DenseNet is a convolutional neural network, CNN, that excels in feature extraction by using dense connections between layers, unlike traditional architectures that simply stack layers. DenseNet connects each layer to all previous layers, promoting feature reuse and improving gradient propagation. In the context of sign language gestures recognition, the DenseNet SVM approach combines feature extraction with DenseNet and classification with a support vector machine. This method involves several steps. Data processing, the images are resized to a standard size of 32 by 32 pixels to reduce complexity. Feature extraction with DenseNet through several convolutional layers and dense blocks. DenseNet extracts features such as contours, edges, shapes, colors, and intensities. Classification with SVM. The features extracted by DenseNet are then provided to an SVM classifier which performs the final classification. So these are our best results for YOLO V10. We got best accuracy for 0.98% with a training time of 4.7 hours, and DenseNet SVM best accuracy is 99.99% with a training time of 1.86 hours. So as you can see, the metrics we used, precision, recall, and the time, of course. Application demonstration. On the model, then we import an image, then we wait for its classification. The result, we can see that the classification worked, and the percentage of the classification is shown. The precision is shown. Conclusion. We have explored how deep learning methods can detect and translate sign language into text. Through our solution only addresses part of the larger goal, key limitations include a real-time detection and translation. Future research could enhance communication between deaf-mute individuals and hearing people by improving model robustness against lighting variation, viewing angles, and low-quality images. Thank you for your attention. I hope you enjoyed the video.